Hello, am I audible? Can anyone respond? Am I audible? Hello, can you hear my voice? I'm audible.
Yes, sir.
Okay, okay, fine. So let us just wait for 2 more minutes. Let some other people also join. Don't expect much people today because match is going on, but still we have to continue the class. So let's just wait for 2 minutes more. Okay, I guess we can start now. So I'll share the screen. So is my screen visible to all of you? Can anybody respond?
Yes, sir. Yes, sir.
Okay, thank you. So we'll start. So this, as you know, the course is, introductory organic chemistry. So basically, it's a general introduction of what is organic chemistry, and the course is designed such a way that it can be intended to a general audience. So I know there may be people attending this course from different levels of their career. Maybe they are UG students, PG, PhD, as well as advanced stages of their career. People are there, but this is intended towards a general audience, so you may have the knowledge already, but we'll still discuss it so that you can, brush up your basics. Also, like it can be enhanced in some way. Okay, so with that we'll start. Uh, so this will be my first lecture for this, first week talk. So how I have, designed this one. So we'll not directly go into the problem solving session. So I will just go, I will take you through a gist of the lectures, whichever was discussed in the first week, and then we can discuss some problem solving approach, right? So we'll start. So organic chemistry, we mainly focus on four element. Okay, and that is carbon, hydrogen, nitrogen, and oxygen. Why? Because these four elements makes the most of the organic compounds. Along with that, you have some other elements also present. You can have phosphorus, sulfur, halides. I can write halides, etc. So this is purely, uh, non-metal elements that are present. So I think someone's mic has not been muted. Can you mute it? I'll just check it. Uh, okay, fine. So it purely consists of non-metal elements. And when you talk about organic chemistry, we mainly consider carbon based molecules, because it was derived based on the carbon compounds. So carbon has a unique property that is called catenation. Okay, catenation means to form multiple chains in between. Okay, and for this you have different allotropes. You maybe definitely must have heard of it. Different allotropes of carbon. Okay, what is the example? You can have sp3 based diamond. Okay, you have sp2 based graphite. Then the single layer that is called graphene. Sorry. Okay. You have carbon shoot, and like many things you have, carbon nanomaterials, like that. So it's mainly a chemistry consisting of carbon molecules. Okay. Now, so in this course, you will be, starting from the basics. You will start from the electronic structure. Then, you will go to the hybridization, the shapes of molecules. So this is actually a recap of what we have been learning, from the beginning of when we started organic chemistry. Okay. So that's why I told that you may have, already have that idea in your mind. You can just brush up yourself, your basics. In an atom, what we have, you have a compact space which is called nucleus, and on the outside you have an orbit where your electrons move around the nucleus. Okay, these are your electrons. And if you consider if you consider a space, suppose this is a space that is covered by the atom. So out of this, your nucleus will be, so out of total volume in space, nucleus will cover very less, around 10%. Okay. And as you know, electron doesn't have any mass. Okay. So almost 90% space will be vacant. So all of your mass is centered at the nucleus, right? Then you have your nucleus, which is positively charged. You have different orbitals, right? And these orbitals are, quantified quantified by quantum numbers, right? You have different quantum numbers, n, l, m, and s. That is called principal. Okay, secondary, magnetic, and spin. Okay, like that. So when you go, you know, from the core to the outer shells, what will happen? Your electrons are getting much more distant from the nucleus. Okay, so as the distance is, increasing, then so this is negative charge. So this attraction is also decreasing, right? Okay, and then your electrons are loosely bound, right? So what we called as valence shell. Okay, valence shell is the outermost most shell. Okay, it is the N. Okay, so what you need to remember is that your valence electrons, suppose you have, your N is equal to 1, you can only have one sigma orbital, that is 1s. If your N is equal to 2, you can have 2s as well as 2p, right? So this is for L equal to 0, this is for L equal to 1, right? If you have N equal to 3, then subsequently we'll have S, P, and D. Okay, like that. So here you have both S and P as your in your valence shell. And the energies of these orbitals, this 1s orbital, 2s, 2p, will all be different. Okay, so based on the so based on the relative energy difference of orbitals, electrons don't, occupy orbitals randomly. They, they just don't occupy the orbitals randomly. So there are some rules. Okay, what are the rules that we'll discuss now? First rule is called Hauber principle. I think every one of us have heard this one in plus two, right? So this principle states that the electrons will go to the lower energy orbitals first, then the higher energy orbitals, right? So you can assume like if it is your 1s, then you have 2s, 2p, 3s, 3p, 3d, okay, 4s, 4p, 4d, okay, 4f, then 5s, 5p, 5p, 5f, 5g, 6s. So how it will fill according to the energy, right? So we generally do it like this way. Okay. So the flow of electron will be in this way. Can we write the order? It will be like 1s, then 2s, then 2p, then 3s, okay, then 3p, 4s, sorry, 3d. Okay, so like that it will go. So one difference you can see here, that 4s is the n equal to 4, this is n equal to 3, but still this 4s energy is much lower. Okay, so this you can study in inorganic chemistry, because it is the property of 3D metals. So for that, 4s energy gets lower compared to 3D orbitals, so that is why 4s is filled faster. Okay, so generally for our purpose, for organic chemistry, we can consider this region. Okay, that will be enough for us. So second principle is, are you following, or is it fast?
No, sir, it's okay.
Okay, thank you. So second principle is Pauli's exclusion. What does it tell? So it tells that at one orbital, okay, the spin of you know uh, two electrons must be opposite. Okay, so it means suppose you have one orbital. Let's say this is 2s. So first electron you can give the direction anywhere or either up or down. But when the second electron will come, it should be always down. Okay, why? Because if your direction is opposite, you can have attraction that leads to lower energy and stabilization. But if you have same energy, same direction of spin, then it will repel. And repel means higher energy and destabilization. And third one is Ohm's rule. It says that if you have some degenerate energy levels, let's say you have three p orbitals on x, y. Can somebody mute your mic? Whoever is unmuted. So if you have three p orbitals along x, y, and z axis, but they are degenerate in energy, right? Then if you have, uh, asymmetric number of electrons. Let's say I have four electrons. So how can I place it? So I can place it like this. That can be one possibility. Or I can place it like this. So what was the difference in my approach? So here I filled the maximum electrons to an orbital first. Then I went to other orbital. But here what I did, I filled one initially to each of the orbital, and then the excess electron I went to put on the orbitals where already one electron is there. So Hund's rule states that if you have degenerate energy orbitals, then you have to put one electrons each first in the degenerate shells, and then if you have excess, then you can go for the pairing. Because in this configuration, much more. So you can see all of the orbitals. Okay, even there is one orbital free to get the electrons, it is vacant. Okay, and in other two there are too much of repulsions. So this will give much higher energy, requirement to form this configuration. Compared to this one, here you have more symmetric filling of electrons, and this leads to lower energy. Okay, always when in same principal quantum number, same shell, you have a number of degenerate energy orbitals. So you fill one first, and then if you have excess, then you go for pairing, not before that. Okay, then so for organic compounds, we deal with peptide orbitals. Okay, rather than pure atomic orbitals, right? What are atomic orbitals? These are mainly your s, p, d, f. G, H, and so on. Okay, so these are your atomic orbitals. But in organic chemistry, you can think of hybrid orbitals, that can form much more stronger bonds, mainly covalent bonds. So covalent bond, as you know, in covalent bonds, suppose you have a or no a homonuclear or heteronuclear bond, okay, where you have contribution from both. Okay, so to form a single bond you need two electrons, right? So one electron is given by this atom, one electron is given by the other atom. Okay, so it's called covalent bond. Same for here also. So this single arrow is meant for single electron donation. So you have some special cases where you will have bond like this. What does it mean? So in these two electrons required for the bond is going from one atom. Okay, so in this case, one is your donor, one is your acceptor. Okay, this is called coordinate bond. Coordinate bond, and this is mostly observed for inorganic complex. This kind of structures in coordination chemistry you must have studied like this. So all these bonds are coordinate bonds, they are not covalent. Okay, and then another case you have electrostatic electrostatic so you know or you can say like ionic bonds, where like your sodium chloride NaCl. So this is just not a normal covalent bond like this organic moiety. So this is not the case. This actually has some ionic interaction. Okay, and they stays together in the space via ionic interaction. This is called ionic bond. So in organic molecules you can have also this kind of effect. Suppose this is called ionic character. You have two atoms connected by a bond, but here comes the term that's called electronegativity. Okay, electronegativity is nothing but ability to attract neighboring electrons, right? So when suppose he in this case your A atom has more electronegativity than B, then what it will happen? It will pull the electrons of B. Okay, it will pull the electrons by the single bond, and then we can write it as this delta negative and delta positive. Okay, and this is called a minus I effect. Okay, when it is pulling. Okay, I for induction. I for induction. So through bond, it can pull the electrons, and so that the electron is going from B, so it will be partially positive. It is coming to A, it will be partially negative. And this one will give some, due to this, some ionic character will be generated in the covalent bond, right? Let me give you one example. You compare between this one, carbon carbon, and any carbon halide bonds, right? Okay, so carbon carbon both has the same electronegativity, okay, but halide has much more electronegativity. No, uh, electronegativity is more than carbon. So what will happen in this case? It has no effect. Okay, it will cancel out, so it will be non-polar. But here, this halide will pull the electrons from carbon. So this will be delta minus, delta plus, and this bond will be polar. Okay. So whenever you can see the difference in electronegativity is more than 0.5. You can consider as polar bond. So sometimes in competitive exams, this kind of preliminary question comes. So they can give you this electronegativity value and can compare, give you to compare between some molecules. Okay, they have some options. So you have to compare like this. Which one is polar, which one is non-polar. Then we move forward. Yeah. So let us continue the discussion about hybrid orbitals. So these hybrid orbitals can be formed by any atoms. Okay, but for our purpose, okay, or better to say understanding, we will consider carbon atom. Okay, so how does it goes? So what are the hybrid orbitals you know of carbon? You might have heard about sp3, sp2, okay, sp like that. Huh? So how they come? Okay, how does they formed? So that we will discuss. So generally for carbon you have 2s, 2p, and 1s. How much electron you have in 1s? 2 electrons. 2s you have 2 electrons, and 2p you have 3 orbitals. You have 2 electrons, right? Okay. So now you can see there is only 2 unpaired electrons present in 2p. Okay. So that cannot form this sp3 hybridization. So for that, this s and p orbitals get mixed. This is called sp mixing. Okay. After mixing, they form something like this. This is your energy coordinate. Okay, just a second. So 1s will not participate, as I showed you already. uh, Show you once again. And yes, so this here, So this n equal to 1, n equal to 2. So all these shells are core shells. They will not participate in bonding. Okay. So just like that, this 1s orbital will not participate in bonding. Only this valence shell orbitals, they will get mixed and they will form. So altogether you have S 1 and 3p. You can have 4 orbitals of mixed character, and according to Hund's rule, they will share each orbital. Okay. So these orbital are represented as, these 4 orbitals are represented as is p3, 1s and p 3p. And how they will look? Their shape is no a tetrahedra. Okay, they will form a tetrahedra, but they have their anti-bonding lobes also like this. Okay, so it's like a, all the lobes are, so it is not getting selected. Okay, so suppose you have like this. Just along the edge of a tetrahedra, the lobes will be placed in space. Okay, so this is a tetrahedra. For sp2, how it will be like? So I will not, I think you have already understood how this is getting formed. So I will just write the final form. 2p, 2s, and 1s. 1s will not participate. So sp2, there will be 3 only, but 1p will be left, right? So how many electrons are there? 4. Okay. So altogether 4 electrons are there. 1, 2, 3. Okay. And how can I place it? I can place it here. So this will remain as separate. So it will look like a triangle. Okay. This is a plane, a planar triangle. And the another p orbital that is remaining, that will be on the top of the plane. Okay. So all will have 1, 1, here also 1. Okay, this will be planar. So this is sp2. Similarly for sp, what it will be like? Same thing. 2s, 2p, 1s. It is not participating. So sp you have 2, then 2p are unhybridized. And by the way, so how you can find this geometry? So in this geometry, there will be least repulsion between these electrons, right? These electrons can repel each other, but in this geometry, there will be least repulsion. So you know of this theory that is called VACPR, okay? Valence shell electron pair repulsion. Okay, electron pair repulsion theory. So what does it tell? Your lone pair repulsion will be much more than lone pair bond pair, then bond pair, right? So all this electron will repel each other. So to minimize the repulsion, they will get to one specific geometry which will be least in energy. So similarly for sp, so you have two orbitals. So it will be like this. This will be linear. Okay. And then you can have two orbitals. Suppose writing one this color, and I will change this. Okay, can you understand this one? So this will be along an axis. You can call it as linear. We can also have electron in these orbitals. Okay, this is the shape of an sp orbital. Now, we'll talk some part about Lewis electron structures, but briefly we'll discuss because you already have heard of it. Okay. So in Lewis structures, you take care of valence shell electrons. Shell electrons, right? General rule is that for hydrogen and helium, of course, so uh, it will maintain two electrons in the sorry in the valence shell to get stabilized. The second row you will have, you know, so all this carbon to halide, all these elements will try to maintain octet in valence shell. Okay, so on and so forth. So now how you can calculate this? Let's say, okay, I'll just discuss this one only. For this nitric acid, okay, how many valence electrons you have? You have for hydrogen 1 electron, nitrogen you have 5 electron, and oxygen you have 3 number. So one each oxygen you have 6 electrons into 3, that means you have 18 electrons. Okay, and how you can place them? So for that, to get the structure, you need to first find out your central atom. Okay. So in this case, central atom will be nitrogen because it can form maximum number of bonds among all of them. So nitrogen is your central atom. Once you are done with the central atom, okay, then you need to uh, draw the preliminary structure. So I will just connect it. Okay. So you need to, apply a little bit of, your chemistry knowledge so that as it is a acid, so there must be some acidic proton. So you can place the hydrogen on the oxygen. Okay. So now you have to complete other things. So 18, so total electron is total valence electron how much? 18 plus 6, that is 24 electrons, and 24 electron means 12 electron pairs. Okay, this can consist
हेलो
of, yes,
सर सर आप पढ़ा रहे हो या रीडिंग लगा रहे हो समझ तो कुछ आ ही नहीं रहा
which part you cannot understand?
सर दिस इज राइट बिकॉज समझ नहीं आ रहा है। आप इंग्लिश में एक्सप्लेन कर रहे हो, आई नो, बट थोड़ा हिंदी में भी समझाइए ना।
ठीक है, आप मेरे को बोल सकते हो कोई भी टाइम पे, मुझे मतलब इंटरप्ट करके बोल सकते हो कौन सा पार्ट नहीं समझ आ रहा है, ठीक है?
यस
सर
सर,
आप
बट मैसेज टेक्स्ट किया था आपने, फिर देखा नहीं।
ओह, एक्चुअली आई एम नॉट एबल टू सी, मैं देख नहीं सकता वो वाला। जस्ट अ सेकंड, एक सेकंड। ओके ओके। सो कौन सा पार्ट में प्रॉब्लम हो रहा है, मुझे बोल सकते हो?
ओके
आपका कौन सा पार्ट में प्रॉब्लम हो रहा है?
सर, प्रॉब्लम ये नहीं कि आप समझा रहे हो, प्रॉब्लम ये है कि हम यूपी बोर्ड से हैं, तो इंग्लिश में हम प्रिपेयर कर रहे हैं, आई नो, बट आप थोड़ा हिंदी में भी एक्सप्लेन कीजिए।
ओके 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 ओके, ये कोई प्रॉब्लम नहीं है, ठीक है। तो मुझे मतलब ऐसे ही, मतलब जिसमें आपका प्रॉब्लम होगा तो मुझे अगर आप बोल दोगे तो कोई मतलब इशू नहीं है, मैं एक्सप्लेन कर दूंगा, ठीक है।
ओके
हाँ, बिकॉज
ओके
मुझे पता नहीं था इसलिए, बिकॉज एक्चुअली ये जनरल ऑडियंस के लिए है, एंड आई थिंक ओरिजिनल लेक्चर भी इंग्लिश में है, सो मैं उसी आइडिया से पढ़ा रहा था। ओके
ओके
फाइन।
ओके
सो इधर क्या हो रहा है एक्चुअली, सो पहले आप लोगों को देखना पड़ेगा। सो आई विल ट्राई टू एक्सप्लेन इन मिक्स्ड लैंग्वेज, इंग्लिश हिंदी। सो आर ऑल कंफर्टेबल विद हिंदी, देन आई कैन एक्सप्लेन इन हिंदी ऑल्सो। इज इट ओके? ठीक है ना?
ओके ओके।
Yes, sir.
ओके। सो जब आप लोग ये कंसीडर करोगे, ये ल्यूइस इलेक्ट्रॉनिक स्ट्रक्चर्स, ओके, तो इधर पहले आप लोगों को ये वैलेंस शेल इलेक्ट्रॉन कितना है वो कंसीडर करना है, ओके। एंड देन डिपेंडिंग ऑन द रो ऑफ द एलिमेंट्स, कौन सा रो पे आपका एलिमेंट है। इफ यू टेक हाइड्रोजन, आप अगर आप हाइड्रोजन ले रहे हो, तो हाइड्रोजन क्या करेगा, अपना अपना वैलेंस शेल पूरा करने के लिए उसको 2 इलेक्ट्रॉन चाहिए, राइट? तो वो हमेशा 2 इलेक्ट्रॉन फुल करेगा। अगर आप नीचे वाला रो पे जाओ, तो लाइक यू हैव दिस बोरोन, बेरिलियम, देन कार्बन टू लास्ट में आपका क्या है, हैलाइड आता है, ठीक है। चैल्कोजेंस देन हैलाइड। सो ये सभी एलिमेंट क्या करेंगे, इनके वैलेंस शेल पूरा करने के लिए ये लोग 8 इलेक्ट्रॉन पूरा करेंगे। सो दे विल मेंटेन दिस ऑक्टेट, ओके। सो फॉर एग्जांपल व्हाट कैन यू डू, सो फर्स्ट आप पहले पूरा वैलेंस इलेक्ट्रॉन जितना है वो काउंट कर लो। तो हाइड्रोजन के लिए आपको पता है कि इसका वैलेंस शेल में 1 इलेक्ट्रॉन रहता है, नाइट्रोजन का कितना रहता है, 5। ओके। सो वैलेंस शेल मतलब नाइट्रोजन का है 2, ओके, n इक्वल टू 2, यू हैव 2s एंड 2p ना। ऑक्सीजन ऑक्सीजन के लिए भी सेम है, आपका एन 2 है, और क्या है आपका ऑर्बिटल्स, 2s एंड 2p, सेम है। सो आप कैलकुलेट कर लो, इसका 5 है इलेक्ट्रॉन वैलेंस में, इसका 6 है। अ,
Are
इधर
you
अपना
comfort in English?
आई एम comfort, बट आई हैव टू some
5.4
Hindi is not correct. You can speak in English only.
Yeah, nowadays in English.
Hello?
Yes, sir. Can you speak English?
Can you speak in English only, not Hindi?
ओके ओके। सो ओके, सो द पीपल, जो लोग मतलब आप बोल रहे हो कि हिंदी के लिए, तो आई विल अपलोड दिस रिकॉर्डेड वीडियो, देन यू कैन चेक इट एंड देन यू कैन अंडरस्टैंड, ओके।
Sorry, can you repeat once again?
Yeah, like the people some time ago they were asking for Hindi. So what I will do, I will upload this session also, so you can recheck it, and that time you can understand. It will be okay, right? I think who asked this one? Um, okay, Dr. Jyoti, right? So तो मैं ये अपलोड कर दूंगा जब उस टाइम पे आप फिर से चेक कर सकते हैं, ठीक है? सो फॉर द जनरल ऑडियंस आई हैव टू टीच इन इंग्लिश ओनली। आई थिंक इट विल बी बेटर। ठीक है मैडम, इट्स ओके। Okay, fine. So after that, when you fix your central atom, you calculate everything. So total valence electron, it is 24. That means you have 12 electron pairs, right? These 12 electron pairs can be lone pair or bond electrons. Okay. So now you can check it. So already you have 1, 2, 3, 4. Okay. 4 bonds means 8 electrons. So you need uh, 8 electrons means 4 electron pair. Now you need to assign the rest 8 electron pairs, right? How can you assign it? So you have to give the lone pair. So this oxygen can have 2 lone pair, okay? And then this oxygen can have 3, this oxygen can have 3, okay? So how many you have assigned? 1, 2, 3, 4, 5, 6, 7, 8, okay? So 4 plus 8 electron pair, you are getting your 12 electron pair. Okay, that was required. We calculated this one. But your structure is not correct. Why? Because you need to take care of the formal charge. Okay, so how does it go? How it will go? So you have this lone pair. Okay, if you this lone pair can be donated to this bond, then it will become like now nitrogen can only make 3 bonds, right? Now it is connected to 4 bonds. So this will be positive and this will be negative. Okay, and then here you have or I can show you the other way. Okay, just a second. So here you have lone pair, so it can be donated to here and then you will get the positive. So there was some problem because so when some electron is donated from an atom, then that one will get positive charge, right? So the flow of electron will be like this. So nitrogen will donate a pair of electron to the bond so that it will get positive and here it will be negative. Okay. Is it correct? Just a second. I may need to check this one, but this should not be here. Okay. This one will stay as negative because it is singly bonded and here are already 2 bonds present. Okay. So this will be a correct structure, but you need to take care of the formal charge. So for this nitrogen or the nitrogen, so how can you calculate this one? Number of valence electrons in that atom. is number of lone pairs, okay, minus half of bonding electrons. So for nitrogen, you have total 5 number of valence electron. Then in this situation, you don't have any lone pair present, okay? And then you have half into how many bonds are there? 1, 2, 3, and 4. So into 4, that means, sorry, 4 bonds means 8 electrons, right? So total 8 electrons. So that means this is 4, 5 minus 4, that is 1. So that's how this positive charge is coming, okay? Single monovalent. So similarly, you can calculate for this one also. So for this one, how it will come? So total number of valence electron is 6 for oxygen. Then number of lone pairs, how much you have? 1, 2, 3, 4. Let me just write it. This one, this minus charge also you can consider as lone pair, okay? It is actually extra lone pair. Okay, then minus half of bonding, one bond you have, that means 2 electron. Okay, that means this is 1, 6, 6 cancel, minus 1. Okay, you got it? This is how you can calculate the formal charges. So I think there were some homeworks given, so I can try to solve that one. This is one. Another one is, so first you can try to draw the structures, how it can look like. Then you have N, 8. So this is your positive charge, huh? And then this bicarbonate, how it should look like. Okay, yes. So what will be your formal charge? It is already given. So this is the structure actually. Okay. So you can follow this method, or you can get to the structure. Hmm.
Okay.
I'll just give you the answer here. Here on the nitrogen, you don't have any lone pair, right? So then you can go for the next one. So there are some molecules that are called electron deficient, okay, or in other language you can call uh, incomplete octet. What are those molecules where your central metal, not metal, sorry, just thought of inorganic chemistry. Yes, so central atom is not complete octet valence shell. Okay, what are the examples? But all kind of boron compounds. Okay, BX3. So X can be chloride, bromide, iodide, etc. And not only boron. So in similar group you have aluminium also. Okay, boron, aluminium, gallium, and so on and so forth. So how it bonds? So boron, what is the electron configuration? 1s2, 2s2, and 2p1. I think yes, boron carbon, yes, 2p1. So then let's say boron trifluoride. Okay, if you see the valence shell electron of fluoride, you will have 7. 1, 2, 3, 4, 5, 6, 7, like that. So here also you can write like this way. Okay, so these electrons it will uh, use to form the bond, right? So boron you have 3, 1, 2, 3. Now this one will be formed. Now the bond will be formed by use of these two. Similarly here, similarly here. Now you check how many valence electron boron has. So this bond 2, 2 and 2. So boron has 6 electrons. Okay, that is why it is incomplete. So what is the general tendency? General tendency is to complete the octet, right? This is the basic, and that is why it is so much reactive. So we are doing lab work in PhD and other things. So when we work in lab with this boron containing compound, let's say BF3, BBR3, okay, BCl3 also. So they are very reactive and they are very dangerous to work with. So we always maintain some specific protocols when we work with these reagents. Also, to store this, to store, you need some uh, protecting agents. You cannot, keep these materials in air. It will blast. It is so reactive with air. It can blast. So normally it is stored in, uh, some solvents that can bond with it, do some electronic bonding, or Lewis acid Lewis base bonding. So normally it is kept in like ether or like normal diethyl ether or some other kind of ether solvent. All this kind of reactive compounds. So then what we can do? Uh, Polarity I have already seen. Yes. Introduce the molecular orbital theory. So from the beginning only I'm discussing the molecular orbitals. So molecular orbitals are hybrid orbitals, okay, mixed from individual individual atomic orbitals, atomic or group orbitals. Yeah, I will show you. Then some of the terms you need to know, that is called bond strength. Okay, also sometimes it is called as a bond dissociation energy. bond dissociation energy. So what is the definition? So the energy given to a system or to a bond to overcome the attraction and cause it to break. Suppose you have the bond AB and I am giving some energy to it so that it will break, okay, and it will be stay as a atom or ions like that. Okay. So basically it will dissociate. So some threshold energy is required, that is called the bond dissociation energy. And this varies for sp3, sp2, sp bond. Why? Because you have different s character. Okay. Why does it depend on s character? You know, s orbital is shaped like this, so it is very close to nucleus. Hmm? P orbital is shaped like this. So you can see if it is your nucleus, there is no electron density. Close to the nucleus, but in S you can have electron density close to the nucleus. So in your hybrid orbital, hybrid orbitals, if your S character is high, if percentage of S is high, then electrons are much more to the close to the nucleus, right? Electrons are attracted by nucleus much more. So they require more energy to break, right? That is why you can see in your sp hybridization you have 50% of S, okay, then you have sp2 where you have how much, 33.3%, then you have sp3 where you have 25% of S character. Okay, that is why sp bond has much more bond dissociation energy compared to sp2 compared to sp3, right? You can understand it, right? And type of bonds can be sigma, okay, can be pi, and for other bonds like delta and all, so these are mainly for metallic. You may have heard about metal bonding, right? So these are higher bonding terms that we don't need for this course. Only sigma and pi will be enough for us. So sigma bond is formed by direct overlap of orbitals, and pi bond is formed by side on overlap of orbitals. How it varies? So direct orbital overlap is something like this. Let's say you have two s orbital. This is your nucleus. You are forming a bond. So let's say this is your hydrogen, H2 molecule. Okay, These are your two 1s orbital. Yeah. So this is called direct bonding. This is called sigma. If you have p or say sp, something like that, so I'll just try to give you example of p. This is p and it is interacting direct. No, this is nucleus, this is nucleus, this is forming a bond here. One electron here, one electron here, one electron, one electron. So these are p orbital. Okay, but when it is colliding head on, okay, this is the direct overlap. Direct overlap, this forming sigma. Now think of another scenario. So better, okay, I'll draw it once again. This is your sigma p orbital, which I've already formed the bond. If you have any doubt, you can stop me and ask, okay, because I cannot see the screen who is writing what. So one of the p orbitals is forming the sigma. Then you have another two, right? You have another two. What is the role of them? You have another two. So this one can form the pi bond. Of course, it has to match the symmetry. Okay. So for pi bond, what you need, same exact same plane. Otherwise, it cannot form the pi bond. So these are called pi bonds. Sorry. These are called pi bond. So, so depending, I already showed you the structure of orbitals or the geometry of orbitals. So sp3 will be like this. These are all hydrogen. All hydrogen. Or sp2 will be like this. Again, these are hydrogen. Okay. Here, all over you have one electron. Sp will be like this. Better I can show you another color. So as you can see it, in sp only one p is being used, so two are free. So two p are free. Okay. So if you have C triple bond C, that will be much more stable bond. Okay. So bond dissociation energy will be higher. So here you have one p free. Okay. So if you have C double bond C, it will be in the middle. And here you have used all of the p orbitals. You have no p orbital left. Okay. So for C single bond C, its energy will be least. Okay. I guess you have understand the point. So just for a typical case, so primary case for hydrogen, you may have come across this potential energy curve. It's a very typical curve that we study always. So this is your distance between atoms. Okay, this is your potential energy. So for hydrogen, this curve follows something similar to this. Okay. This is the nature of the potential energy that vary according to the distance. So in this case, when your two hydrogen atoms are well separated, okay, these are well separated. So there is no interaction between them. So potential energy remains zero. This is zero. Okay. So you come close to at some point where at this position you will have some interaction going on between them because electron is negative, nucleus is positive. There will be some interaction, for that your potential energy will be low. Okay. Also some van der Waal attraction will occur. So this is where your two atom will be start fuse to form a molecule. Okay, this is the point. Then you will come to a point. You will come to a point where your energy will be minimum. Minimum potential energy. Okay. And at this point, it will form the molecule. It will be perfectly overlap. Okay. Why? There are two contributions. Okay. One is two factors. One factor is electron repulsion. Okay. Another is uh, nucleus, not nucleus. Mostly it will be van der Waal because that is too far apart. It's attraction. Okay. So these two effects are contrary. They are opposite to each other. So at some part of time, the attraction will be dominating over the repulsion. That is why in this range, the energy will decrease. Okay. After some time, if you try to compress it again, if you try to make the distance more closer, then the electron repulsion will dominate. So the energy will be higher. So at this point only, it will be the optimum case, where you will observe this molecule and the distance will be around 0.75 angstrom, okay, between two atoms. So now you need to look for bonding and anti-bonding orbital. So suppose you have this 1s orbital of hydrogen, you have this 1s orbital of hydrogen. This is one electron, this is one electron. When they will combine, they will form two energy levels. One will be lower in energy, one will be higher in energy. This will be like plus, this will be plus, minus. What is this plus? What is this minus? This is not the charge. Okay. This is the phase of orbital wave function. So whenever we are talking about overlap, overlap considers orbital wave function, that is represented in phi. Sorry, not phi, psi. Okay. So this one can give us information about size, okay, then shape and phase of the orbital. So F function is very important in terms of molecular orbital theory whenever you're studying. So in this course, it is not described much in detail, but if you do some advanced organic courses, you will be studying these orbital F functions. Okay. So simple idea is that if both of your orbitals are in the same phase, okay, or same, a positive or negative sign, same phase or same sign, then it will be less energy. Less energy means favorable overlap. Favorable overlap. If the phase is different, if different phase, like in this case, plus and minus, it will be of higher energy. Energy unfavorable overlap, right? So that is why it will be at lower energy. So we have two electrons. We can fill it like this, one and then two. This is the orbital diagram of hydrogen. Okay. And then I've shown you everything. Okay. So for so let's say we are consider another atom then carbon. We have discussed much more about carbon. So this time we will consider nitrogen. What is the electron configuration? 1s2, 2s2, 2p3. So general configuration will be 1s, 2s, and 2p, right? If you mix it, then what will happen? 1s will not participate, and this mixed orbital, you have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So what you have three orbitals that can form bond. Okay. So you have sp3. Okay. This is sp3. Now, similar to sp3, it will form a tetrahedra. Right. I will not show the antibonding lobes. Okay, you can understand it. There are small lobes opposite to this one, that is antibonding. I will not show it. So everywhere, so suppose this one you have 1, 1, 1, 1. And if you now combine with hydrogen, it can form the bond. So this is the structure of ammonia. Now compared to methane, we have H here, H, H and H. So can you just tell me what will be the difference between the bond angles? Any idea? I have already discussed these things. Because as per BSEPR theory, lone pair greater than lone pair, bond pair greater than bond pair, right? This is the order. So you can see lone pair will repel much more. So this will be 112 degree around. Okay. And this will be exactly tetrahedral, that is exactly the same angle for the tetrahedron. Okay.
Sir, what is the angle of hydrogen, sir?
This will be relative. So if it is ideal, say this is 109, this will be less than 109. So maybe it can be, 95 to 100. I'm not sure the exact, but it will be like this. Okay. Because it
Sir,
is
it is
repel
around 107 degrees, sir.
for which one?
In ammonia, the angle between the hydrogen bond is
Yeah,
107
that's
degrees.
what like the exact one I don't remember right now, but it will be less than the ideal case. Okay. Because it is pushing the lone pair is pushing the bonds. Okay, so that effect is much more great, so that this angle will be more and this angle will be compressed. Okay. Okay, you can check it, you can check the absolute value, but it will be less than the ideal case, right? That's what the concept is. And then so you can have a special effect that is called mesomeric effect, or in simple term we can know as resonance effect. Okay, what is a resonance effect? So electron can move with orbitals of allowed not geometry. So energy and to, to stabilize the system. Okay, so let's say uh, you have this system, it's this simple benzene ring, okay, and you have this phenol. Okay, you have the wedge attachment. This electron can easily go into the conjugated bond, and then how it will look like. It will be positive, negative, then like this. So you can distinguish by this arrow, double-headed arrow. Between resonance structures. So you can from the minus here, can go back to here. And you can finally get the initial form. Okay. So this lone pair can be, uh, can move along the conjugation. Okay. So that to make different resonance hybrids. So these are called not resonance hybrids. So resonance, resonance isomers or something. Resonance structures. It can be called as mesomers. Okay. So the stability of your compound depends on how many number of resonance structures you have. Okay, and you can represent all these structures in a single form, which is called resonance hybrid, and that will be like this, which you have. Now you can see this bond has both single and double bond character. Hmm. These all bonds have single and double bond character. Now, wherever we can see that minus charge is going, so that has a partial negative charge, and this oxygen can have partial positive charge. Okay, like that, resonance hybrid can be represented. Okay, so I think we are done with the conceptual studies. Then we can start some problem discussion. Okay.
Sir, I can't understand the structure. Can you
Yes, yes.
explain again that?
Tell me.
Sir, actually I can't understand.
So,
Can you
resonance
explain
is,
again?
say you have a conjugated type of system, okay? And then you have something like this, okay? So this electron can move. This electron can move through the periphery, through the conjugation, so that you can get this one, this structure. Okay. So this is, the effect of electrons to, stabilize the system. So all this carbon, you can see all these carbons have p orbitals, right? All are having p orbitals. Hmm. So if your electron can just juggle between all this orbital, then what you can have, you can have extra stability, because extra electron means you have energy, more energy. So if this electron you can stabilize through this, isomerization, then it will have more stability in the system. So for this resonance to have, you need to have requirements. I will write it here. Write it.
Thank you, sir.
No, I'll write it. What are the requirements?
Sir,
Yes.
sir, can you explain with it benzyl alcohol?
Sorry.
Sir, can you explain it with a benzyl alcohol?
Benzyl alcohol.
Yes, sir.
Okay, okay. Just let me try. Benzyl means you have CH2OH, right?
Yes, sir. Yes, sir.
In this case, you see, you can have one carbon that is sp3 hybridized. Okay.
Yes, sir.
So there is a break in the conjugation. So for conjugation, you need to have this, subsequent p orbitals in your along the conjugation. So this one you need actually. So if your conjugation is breaking somewhere, so whenever you are having sp3 means you are using all the px, py, and pz. All you are using. You have no vacant p. You need sp2 that has at least one vacant p. Okay, that is not participating in the hybridization. Otherwise, where you will accommodate that electron, right? You need one vacant p orbital. Okay.
Sir, so you said mesomeric effect or not? occurred in the benzyl alcohol. Yes, sir.
Do you have any other example?
No, sir.
Because you need some vacant p orbital, right? Because you need to
Yes,
accommodate
sir. I
the
understand.
electron. So
Yes, sir. I understand.
sp2 it can work. Okay. So then we can discuss some of the problems. So not only like I have shown you where the electron is going into the system, so it can also take out the electron. Let's say you ever having okay. So you told me a benzyl alcohol, so I will tell you this one, that benzylic cation. Okay, like this. So in this case, you can have it because this one can go here. Hmm? Then you will have this kind. This CH2 will be here. This will be positive. This can go here. You will have positive here. CH2. Then again can go to here. CH2. And we can get to the initial structure where we started. Okay, like this. So uh, the full resonance hybrid will be something like this. CH2. So everywhere you have some double bond character. Okay, and these positions will have partial positive charge, right? So whichever is the effect, if you are moving electrons or if you are
That is, sir.
transferring electrons to one vacant site or the positive side, so you need to have p orbitals in there. Okay, otherwise it cannot accommodate the electrons which is moving. So let us discuss some of the problems which were uh, either from the previous year questions or I have just gathered it. So here is one. This is the nitrate structure. Yeah. So you need to calculate. So I can label this one. This is O1. This is O2. The question is calculate formal charge of not O1. Sorry, O2. It will be O1. It is very easy. So this is the questions. Can you try it? I will give you the options. You try it. Very easy questions. So let me write the formula. Yes, it is right. So number of valence electron minus number of non-bonded electron, okay, minus half of number of bonding electron. A non-bonding electron, that means your lone pair. So you have oxygen for the moment. So 6 valence electron. How many you have? 1, 2, 3, 4, 6. And then you have one bond here into 2. And it is -1. This will be right answer. Okay. Let's move to next question. So draw the Lewis structure of CLF. And
थोड़ा धीरे करिए.
okay, find out the formal charge. This one you have noted or not?
Yes, sir.
Don't worry, because all this slide I will upload, so you can get these slides after some time. Okay, after 1-2 days you can get this slide. Find out the formal charge of both Cl and F. This is the question. Can you try it? This has no option.
Zero, zero.
And Lewis structure. Okay, I can help you. So Cl, you have 7 electrons in the valence. 1, 2, 3, 4, 5, 6, 7. Similarly, I can write for fluorine. So these two will be used for the bonding. Okay, so that it will form the sigma bond. Okay, and if we calculate for chlorine, it will be 7 minus how many? 1, 2, 3, 4, 6. Then minus half into 2. Yeah, and 7 minus, sorry, 7 minus 6 minus 1, that is coming 0. So same will be for fluorine also. Okay, this is also 0, this is also 0. Okay, let us move to next question. So this is a compound. Given compound is IF3. So draw the Lewis structure and uh, valence electron of central atom. This is the question. So can you tell me which one is the central atom here?
Iodine, sir.
What is the reason? Reason behind it? So this iodine, okay, or
Octet was not completed, sir.
no. You mistaken. So this is not the same case. So this is not deficient octet. It is more than octet. Okay, this is called expansion of octet. So all these elements like iodine, bromine, so which has
It has
three,
peripheral atoms, sir.
huh?
It has many peripheral atoms, sir. So I think it will be the central atom.
Yeah. So the reason behind that is it has 3D. Okay. So you cannot see 3D for the first or second row elements, right? So whenever you have 3D inside, so it can accommodate electrons. Okay, and that's why these atoms can expand octet. Okay, even there is more than 8 electrons, they can accommodate it because of the underlying inside 3D orbital. So it will be like this is iodine, right? 3 of fluorine. Let us see. One. Okay. Now, similar for this one, 2, 3, 4, 5. 1, 2, 3, 4, 5, 7. Okay. So now what you can do, you can form the bonds here. So you have formed your compound. And how many electrons you have? You have here 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
इसमें आवाज
5,
जाती है
6.
बेटा आप शांत
So now you see, you have 2, you have 4. From the bond you can get 2, right? Each bond means 2. Here 2, here 2, here 2. How many are total? There are 10 electrons. It is more than 8. What was supposed to be there, but it is expanding the octet. Okay. So if you compare, like IF3 and ClF3, okay, which one will be more stable? This one. Why? Because it has a, one is, it is down the group to chlorine, so it is more weak, in size, so it can accommodate more number of atoms, or uh, that is bonding atoms it can accommodate. And another one is the inclusion of 3D. So Cl also has 3D, but due to the size effect of iodine, it will be much more stable. So two effect is there. One is underlying orbitals that can accommodate electron, and one is the size. Okay. Then next will be, okay. So in methyl anion, that is your CH3 minus. Okay. Determine the orbital where the negative charge is occupied. Okay, so you need to determine where this negative charge is staying. Okay. So first you can try for the hybridization. Hybridization is half into valence electron. Okay. Then monovalent atoms bonded. Then number of cations plus number of anions. So half into valence electron for carbon is 4, right? How many monovalent atoms? 3. Then you don't have any cation, but you have one anion, so that is 1. So half into 8, that means 4. 4 means sp3, right? This is the hybridization. Now you draw it. If you draw it, so 3 will be connected to hydrogen. We'll have the unpaired electrons here. Okay. And this negative charge, that means 2 electron, will be staying at this orbital. This is which orbital? This is sp3 only. Okay, one of the sp3 orbital. Okay, this is the location of the negative charge. Okay. Then this is the last question that we will discuss today. So calculate the steric number, the following compounds. Okay, what are the compounds? One is propane. Okay, so for the methylene carbon, you calculate the steric number, and another one is carbon dioxide. For this carbon, you calculate the steric number. What is steric number, by the way? Do you have any idea? Steric number? Huh? Do you have any idea what is steric number?
No,
The
sir.
bulky groups present around the atom.
Not bulky, any group. So steric means what come to your mind, steric. So steric means uh, the space, how the space is filled. Okay, direction. That is what how the space is filled. Okay, this is called the steric thing. So then, suppose you have carbon. This is what sp3. Okay. So in this case, how many direction you have? You have 4. So in sp3 you have 4. This is your steric number. Okay. So in these positions, you may have any atom, you may have any lone pair, right? So steric number means number of lone pair, okay, plus number of bonded atoms. So people sometimes they do some silly mistake. What is the mistake? So see, you have to be concerned about the geometry only. Okay. So whenever there is like this, so here you have some other R1, R2 group. In this case, your steric number is 3. Okay. Sometimes what people do, they will take this bond. So here are two bonds. One is sigma, one is phi. So they will take it as 2. But it is not like that. So you have to take only the geometry in consideration. So suppose for nitrogen, suppose for ammonia, your steric number will be 4. Why? Because you have one lone pair plus 3 bonded atom. So you just have to consider in space how your atom is connected to the surrounding. Maybe it is lone pair, maybe it is other atom. Okay, you just to check. So what will be in this case? You have 2 hydrogen and 2 carbon connected to this. So steric number will be 4. Okay, it is sp3 carbon. For here, what will be your steric number? It will be 2, right? For the carbon, because this carbon is sp hybridized. It is a linear geometry. So already you have 2 oxygen at 2 positions. So it is 2. If you consider this one for oxygen, What will be the steric number?
3.
Hmm? Yes. So this steric number will be 3. So this is generally you need to consider only the geometry. Okay, how the space is filled in space.
Sir, what's the carbocation, sir?
Carbocation.
Yes, sir.
So something let's say you have methane. Okay, so like all these are filled. See, you just remove one proton, okay, with the electron. So if you remove this one with the electron, then this position will be vacant. Okay, here is no electron in this sp3 lobe. This will stay as a positive charge. So this is your carbocation for carbon-based molecule. Similarly for sp2, suppose you have CH2 and bonded to some other R2. Then sometimes CH2 will it work? Just a second. Okay, let's say this benzyl cation only. Yeah, you have this phenyl ring here. So here also you have, so this is also sp3 hybridized.
Propylium ion.
Sorry?
No, sir.
Okay, so this is also sp3 hybridized. You have uh, 3 directions occupied by the group. Okay, this is, I can write as phenyl also, and this lobe is empty. This is acting as a vacant orbital. Not vacant, it is positively charged. So this is how when we break a bond,
Sir, is it from propylium ion?
tropylium ion.
Yes, sir.
Tropylium ion, I need to check it. Sometimes it is possible, but what are the requirements? I may need to check it one more time. Okay.
Okay, sir.
But generally, if you form tropylium ion or if you do some resonance, so that is actually stabilizing your positive charge, right? It actually stabilizes the positive charge, so it get delocalized in the molecule. Whatever way, if it is forming tropylium or the resonance structure is, getting forward. So main thing is that if you, so this is the bond, homometallic or heterometallic. If you remove the bond with the electrons, so which one will be more electronegative? That atom will take it. Okay, so it will be a minus, the other one will be B plus, like that. It depends on the electronegativity. So like say you have carbon nitrogen. Okay, so when you are breaking this bond and telling that carbon will get negative, nitrogen will get positive, this cannot happen because nitrogen has much more electronegativity than carbon, right? So this one should not happen. Always it should be like carbon will be positive, sorry, carbon will be positive and nitrogen should be negative. Always it should be like this way. So it depends on the electronegativity also. Okay. So I hope you understand.
Sir, one last doubt, sir.
Ah,
Sir, in the case of carbon radicals, their the steric numbers are in fraction?
for carbon,
Radicals, sir.
carbon radicals. So for radical cases, what is the formula you have? You have like this one, right? CR2, then you have something like this, right? So are you sure where they are placed, the electrons? Fraction.
So we can choose the example as methyl radical CH3.
Okay, this one you are talking about.
Yes, sir. What is the steric number of this?
Okay, let me just try it. So it will be like this. Suppose this is your methane. So for radical cases, it don't break asymmetrically, it breaks symmetrically, right? So single electron will go. So it will form this hydrogen radical plus C. And the lobe will be occupied by one electron. So I think the steric number will be same as your the initial molecule. Okay, because in that orbital, all one electron is going to be present anyhow. Do you agree?
Sir, but that electron occupy the orbital, sir.
Yeah, electron will occupy the orbital.
So why are we consider it as one like lone pair?
No, like electron, no. It will stay at some place, right? It needs some place to accommodate. Okay, so it will definitely go to an orbital if there is any electron present. Okay, do you agree?
Okay, sir.
Better, I will check it also one more time, and next class I can clear your doubt. Okay, so I will check it also once more
Okay, sir. Okay.
because, so I think that if there is any electron present, then it must have any some place to accommodate. So if there is any orbital available, it must be going in that orbital. Okay,
Yes, sir. Okay, sir.
I will just check and reply back in the next class. Okay, I will just start with this one. So I think that is okay for today. And then we'll meet at the next class. Okay, so I'll share the screen, and I'll upload this recorded video as well as the slides that I made today. Maybe you will get within 1 2 days. So thank you all. Thank you everyone.
Thank you, sir.
अगर